Chapter 1. Money can vanish from a transfer when nothing ties the steps together. This is Wallet Services transfer method, a plain Spring service, no @transactional anywhere. It calls debit on the sender, then credit on the receiver. Watch this sequence. Debit commits the instant it finishes, completely separate from credit, which hits a receiver account that's already closed. Run it, and here's the console. Debit commits fine, but credit throws. The receiver's account is already closed. Check the balances after. The sender is down $150. The receiver never got a cent. That money just disappeared. This isn't a rare edge case. Anytime that second call fails after the first already committed, this exact outcome is guaranteed. Nothing links these two calls together. No shared boundary, nothing to undo debit if credit fails. That gap is exactly what comes next. Chapter 2. Transactional Basics. Let's fix the transfer method so it either completes entirely or doesn't happen at all. The fix is a single line. We add the transactional annotation directly above transfer, right where the method is declared. That annotation tells Spring, at startup, wrap wallet service in a proxy object that sits between callers and the real code. Every outside call to transfer hits this proxy first, never the real method directly. Before anything else runs, the proxy opens a database transaction. Only then does it call into the real method body, which does the debit and credit just like before. If both calls succeed without throwing, control returns to the proxy. The proxy commits everything the method did, debit and credit, as one unit. But it has another option. Instead of committing, it can undo everything the method did. That's next. Let's rerun the exact Chapter 1 failure. Sender 42, receiver 99, $150, with transfer now @transactional. Watch what happens when credit throws. The proxy immediately rolls back the transaction. Sender 42 and receiver 99 both come out untouched. Compare that to Chapter 1. The same crash left sender 42 down $150 with nothing credited. Now both accounts stay untouched. The receiver account closed exception, thrown inside credit, propagates all the way out of transfer, right into the proxy. The proxy catches it before it ever reaches your calling code, and immediately tells the database to roll back. The database undoes every change made since the transaction began, including the staged debit. Here's the exact rule driving that rollback. By default, Spring's proxy only rolls back automatically on unchecked exceptions, runtime exception, and error. So what happens if transfer throws a checked exception instead, like an IO exception? Does the proxy still roll back, or just commit anyway? Next up, what happens when the exception you throw isn't a runtime exception at all? We're adding a new checked exception, insufficient funds exception, thrown when a post-debit balance check finds the sender negative. Here's the updated transfer. It debits the sender first, checks the resulting balance, then throws this checked exception before crediting the receiver. We run it. The debit executes, the balance check fails, an insufficient funds exception is thrown, but the transaction still commits. Sender 42 ends up -50. Receiver 99 got nothing, despite @transactional being right there. Spring's default rollback rule only watches for unchecked exceptions. A checked exception looks like a normal outcome, so it commits. The fix: tell the annotation explicitly that this checked exception should also trigger a rollback, not just unchecked ones. We rerun the same failing case. This time the debit rolls back too, right where it started. Chapter 4. The Self-Invocation Trap. Wallet Service gets one more addition, and it reveals a common transactional mistake. Right after the credit succeeds, transfer now calls record audit entry using this calling that method on the current wallet service object itself. Record audit entry carries its own @transactional annotation set to requires new, meaning it should always commit in a fresh transaction of its own. Run transfer and check the transaction logs. Record audit entry never gets its own transaction. It just runs inside transfer's already open one. The caller invokes transfer, and that call reaches Spring's proxy first, not the real object. The proxy opens a transaction, then hands off to the real transfer method inside the bean. Calling record audit entry with this is a direct call on the current object. It skips the proxy entirely. Because the proxy is skipped, requires new on record audit entry is never triggered. This pattern has a name, self-invocation, an everyday call that Spring's proxy never gets to see. The fix: pull record audit entry out of wallet service completely and give it its own audit service bean. Now inject audit service into wallet services constructor right alongside the existing wallet repository, so Spring wires in the real bean automatically. Swap that self call for a call through the injected audit service reference. The call now leaves wallet service and passes through audit service's own Spring proxy. This time, the call goes out to audit service's proxy object, not straight to a method on the same class. The proxy intercepts the call and opens a real transactional boundary before handing off to the actual method body. The audit entry actually gets written inside a transaction, genuinely executing as Spring intends, not silently riding along inside transfer's transaction. Record audit entry genuinely runs now, but it's still plain @transactional with default propagation. So, what actually happens to that audit row if transfer itself fails and rolls back? Chapter 5, Propagation. We'll see whether the audit row survives when transfer itself fails and rolls back. Let's trigger that same failing transfer again. Sender's balance is only 100, and audit service is now properly wired in. Look at audit service.record audit entry. It's just marked @transactional with no propagation value, so Spring falls back to its default, required. Required is Spring's default. If a transaction is already open when this method is called, join it. Don't start a new one. The caller kicks off transfer with sender 42, receiver 99, and $500. Transfer opens its own transaction before doing anything else. It debits the sender's account by 500, staged inside that transaction. The balance check catches the sender going negative and throws insufficient funds exception. Transfer still calls record audit entry, and because required just joins, it joins transfer's already open transaction instead of starting its own. The audit row gets staged in that exact same shared transaction, not a separate one. Transfer's own failure rolls back the whole transaction it opened. Because the audit row was staged inside that same transaction, it gets wiped out right along with the debit. Run it, and the log confirms it. The debit rolls back, and so does the audit row. The failed attempt leaves absolutely no trace behind. The whole point of an audit log is surviving failure. Right now it can't survive the exact failure it's meant to record. Here's the fix. Change record audit entries annotation from plain @transactional to @transactional with propagation equals requires new, a completely different transaction behavior. Requires new suspends the caller's transaction, opens a brand new independent one, and commits it fully before control returns to the caller. The same failing transfer kicks off again. Sender 42, receiver 99, $500. Transfer opens its own transaction first, exactly like before. Transfer calls record audit entry, but now that method demands its own transaction. Spring suspends transfer's transaction, pausing it in place before record audit entry runs. Record audit entry opens a brand new, completely independent transaction of its own. It saves the audit row and commits that new transaction fully, right then and there. Only after that commit finishes does transfer's original transaction resume where it left off. The balance check still fails, so transfer rolls back, but only its own transaction, not the audit one. Run the same failing transfer again. The log now shows the audit row surviving, even as transfer itself still rolls back. The takeaway: required ties a method's fate to its caller. Requires new gives it a fate of its own, independent of the caller's outcome. We've wrapped up transfers. Now let's look at read-only queries and a subtle locking bug. Meet a new method. Get balance. It's marked @transactional with read-only equals true, since it only reads data and never changes it. Read-only is purely a performance hint. Spring skips dirty checking and flush logic. It does nothing to protect against concurrent writes elsewhere. Sender account 42 starts with a balance of $100. T1 reads that balance into its own view, $100. At nearly the same moment, T2 reads that same starting balance. T1 checks 100 against its $80 transfer, and the check passes. T2 checks the same 100 against its own $80 transfer. It also passes. T1 debits $80 and commits, dropping the real balance to 20. T2 then debits its own 80 against the 100 it read, commits, and pushes the sender to -60. The fix is a repository method that locks the sender's row for the whole transaction, not just reads it. Inside transfer, the plain repository read is swapped for find by ID for update, before the balance check even runs. Whichever transaction reaches this row first holds the right lock until commit or rollback. Anyone else waits. T1 calls find by ID for update on account 42 and grabs the right lock first. T2 makes the same call moments later, but the row is already locked, so it just waits. T1's check passes against the real $100 balance, so it debits 80 and commits. Committing releases the lock and drops the real balance to $20. Only now does T2 get through and read that balance, $20, not the stale 100 from before. 20 is less than T2's $80 transfer, so the check fails and the sender is never overdrawn. Under lighter contention, most teams reach for an optimistic version field instead. Same correctness. Caller retries when it conflicts. Two unrelated writes with no transaction around them can leave a system in a half-finished state. Transactional wraps a method in a proxy that commits or rolls back everything it did as one unit. Only unchecked exceptions roll back by default. Use rollbackFor for checked exceptions that should too. Calling a transactional method via this dot inside the same class skips the proxy entirely. Default propagation required ties a method's fate to its caller. Requires new gives it an independent one. Read only is a performance hint, not a concurrency guarantee. Use locking for that. Try wiring up this wallet service example and check out another video here.